In this section of the course, we're going to start looking at discriminative models. We're going to look at how they contrast with generative models that we've looked at so far, and in particular go through a detailed examination of maximum entropy models. So far we've been looking at generative models. In particular, we've looked at language models and naive Bayes models. But in addition to these kind of generative models, there's now much use of conditional or discriminative models in natural language processing, and also in related fields like speech and information retrieval or machine learning more generally. And that's for a couple of good reasons. These models tend to have very high accuracy performance, and also they're linguistically interesting because they make it easy to include lots of linguistically important features. And hence they easily allow the building of language-independent, retargetable NLP systems. So let me now contrast joint versus discriminative models. In both cases, we're going to assume that we have some data DC of paired observations of the data D and the hidden classes C. And so the defining characteristic of joint models is that they place probabilities over both the observed data and the hidden stuff. So we have the probability of C and D. And commonly the way that that's done is as a generative model. So the generative models generate the observed data from the hidden stuff. These kind of joint or generative models comprise all the classic statistical NLP models, not only the n-gram models and naive Bayes classifiers that we've seen already, but also hidden Markov models, probabilistic context-free grammars, and the IBM machine translation alignment models. In contrast, discriminative or conditional models more directly target the classification decision that we want to make. Formally, they put probability distributions that are conditional, the probability of the class given the data. Discriminative models include logistic regression, or in general the whole area of conditional log linear models, including in particular maximum entropy models and their generalization to sequences, conditional random fields. Many other machine learning methods such as SVMs, perceptrons or averaged perceptrons are also discriminative classifiers, but they're not directly probabilistic models. One way of showing the difference between the two model classes is by means of the graphical model diagrams that are used for probabilistic models in general. In these diagrams, we draw circles for random variables and lines for direct dependencies between them. And some of the variables are normally observed and others are hidden. And then for each node is like a little classifier based on its incoming arcs. If we draw these kind of models, what we find is that for a naive Bayes model, the picture looks like this. So at classification time, we are observing the various words of the document, which is our given data, and based on those, we want to predict the class. But in terms of the probabilistic model, our probability factors are a prior probability of the class, and then the probability of the words in the document given the class. And so that we have this generative direction in which the words are generated from the class, rather than actually predicting what we haven't observed. In a discriminative model, such as logistic regression, the situation is the opposite. We've again observed the words of the document and want to predict the class, but this time we're directly putting a probability over the class given all of the data that we've observed, D1, D2, D3. So in generative models, we look at the joint probability over the data and the class, and what we try and do is attempt to maximize this joint likelihood. And as we've already seen, that for categorical models, it's trivial to optimize the joint likelihood. All we do is take the relative frequencies of different events. That is, we count how often different things occur, and then we divide by a normalizing denominator, and we're done. So that's very practical for estimation. In contrast, the conditional model, we want to work out these probabilities of C given D. And so in a conditional model, what we'll do is attempt to directly maximize the conditional likelihood, the probability of the classes observed given the data. As we'll see, this turns out to be much harder to do, but is perhaps more useful because it's more directly related to classification success or error. This slide gives some initial motivation for being interested in conditional models by showing that they have high performance. In this slide, I show the results of some experiments done by Dan Klein and me in 2002. The task here was word sense disambiguation, but essentially that's the same task as text classification that we've looked at earlier, that you're wanting to choose one of a number of senses of words, such as for star, whether it's a rock star or in this astronomical object, based on the evidence of the words around it that you see in the document. And in these experiments, what we were very careful to do is to set up two models which were exactly the same in all respects. They had exactly the same features, exactly the same methods of smoothing the data, but differed only in whether we were doing conditional estimation or joint estimation. And what do we see in the results of these experiments? What we see is, well, if we just skip first of all straight to how it performs on the test data, we see the good news story for conditional likelihood. The conditional likelihood is giving us performance that's 2.5% better than what we got from the joint likelihood naive Bayes model. So this joint likelihood model is a naive Bayes model. And so that's a nice gain and something that is very appealing when building practical NLP systems. Incidentally, we can also notice something interesting by looking at performance on the training set. If we look at performance on the training set, the joint model gets 86.5%, which goes up to 98.5% for the conditional likelihood model. You could think that that's good news, but it's also actually a cause for worry. What you will find is that conditional models can very easily memorize much of a training set, and so they're very prone to overfitting by memorizing too much what happened to be seen in training data, which may not reappear in test data. And so we'll go on and look at how to control this kind of overfitting later on in this discussion. Okay, that's a motivating introduction for discriminative models and discriminative estimation. In the next section, we'll start looking at how we can define the features that are used in these models, and then go from there into the details of how they're estimated.